So it says simplify the square root of 32, and it'd be nice to punch this into the calculator and get the decimal, which you could do. That's not what it wants. It wants it simplified, but it wants the exact answer, meaning we don't want the decimal. If you change a square root into a decimal, it's automatically rounded because those decimals go on forever without repeating or terminating. And so you can imagine how fun it would be to try to get to the end. So when it says simplify these, it's now saying it wants a square root in the answer. Now, if 32 was a perfect square, we would say, oh, it's just a number. But this one is not, right? We know the perfect squares from yesterday. We have them all memorized because that's what we do, and we love to memorize all those. But anyways, there's two ways to do this, so I'm going to show a couple ways. And then you kind of decide which way you like the best. I'm gonna use mostly the second way when we're dealing with square roots. So the first way, let's label this one so we know we're dealing with. So let me do it. This is prime factorization. Now, if you don't remember what prime factorization is, that's okay. But hopefully you'll remember soon how much you enjoyed it. So what we do is we take 32 and we just want two factors of 32. Doesn't really matter what they are. But we're trying to narrow or break everything down into its own prime factors. Now, we've been doing a lot of factoring, which is pretty much what we're talking about. A factor in a multiplication problem is a value that is being multiplied. In other words, 32, for example, you could, and I'm just using one set.
4 times 8.
4 times 8 would be one of them. Okay, now neither of those are prime though. Okay, which means you can break them up even further. If they were prime, we would circle them. So this is kind of like a prime factorization. Some people call it a prime factorization tree, and that's fine. But 4, for example, splits up into 2 and 2, both of which are prime. So we circle those. And then 8, I would split up into probably 2 and 4. You could say 4 and 2, it's the same thing, by the way. And then 4 splits up into 2 and 2, okay? So we end up with a bunch of factors here, 2s, all 2s right here, and that's okay. These are all prime factors of 32, meaning instead of writing this as the square root of 32, what I'm going to do is I'm going to write it now as the square root of 2 times 2 times 2 times 2 times 2. An exponent would work on this one. So I guess maybe I'll even do this 3 different ways. But from here, since we were looking at a square root, right, this means I need pairs. I need pairs, matching pairs, because matching pairs are perfect squares. All right, well, that's not hard to do. I see I've got 2 times 2, which would be 4. In fact, here's what I'm going to do. I'm going to do this with a lot more work than you'd probably ever want to do or use. But I'm going to use it anyways. So 2 times 2 right there, that would be the square root of 4. Now, do we know what the square root of 4 is? It's 2. Okay, so that's what we mean by if you find pairs here, you're looking at a perfect square. In fact, we have another set. These 2 2s right there, which is another, see if I can do this right, it's another square root of 4, which is 2. Well, the problem that we have right now is that this 2 does not have another 2 to pair with to make it a perfect square, which means that it stays on its own as its own square root of 2. So we write it in down here as part of our simplified form as a square root of 2. So this stuff right here that I just did, by splitting this up, that's kind of what that last slide was talking about, is once you get these factored out into what we're looking at is perfect squares in this case, you can separate those from the other factors, okay? So 2 times 2 is 4, 2 times 2 is 4. These ones just happen to be the same. They won't always. Now this would be pretty well simplified. It's almost finished, by the way. What we need is to multiply anything that can be multiplied, such as 2 and 2, which is 4. And then we'll just finish by multiplying that by the square root of 2. And this is our final answer right there, simplified. So I'm gonna use another method here. Some students really like prime factorization, and if that's you, don't worry about these other two methods. You can still watch, if you find that you like one of the others, then use it. But other than that, don't worry about it, okay? Because prime factorization will always work. Even if I don't use prime factorization in the way that I simplify them, but you like prime factorization, use it, okay? Now, the other way to do this, just like we've done with factoring trinomials, is you kind of look for a factor pair that works for, like you wanted the sum of the factor pairs to add up to the middle coefficient. We're kind of doing the same thing here, but we want to look at the factor pairs of these where one of the factors is a perfect square, because it usually is. And if that happens, if we find the biggest one, the biggest perfect square, then we just square root that and then we can be done. So here's what I mean, is let's just look at factor pairs of 32. Okay, so 1 and 32, we look at those. Is either of those a perfect square? Sure, 1 is. But this isn't really gonna help us, right? I can just pull out a phantom 1 right there and then that's good. So we don't actually ever look at 1 in the value we're looking at, kind of like we would with factoring trinomials. So we'll start in this case with 2 and, I'm gonna do it like this, 2 and 16. Okay, so I know that 16 is a perfect square. How do I know that? Because I enjoy memorizing all of these math nerd facts, and so I just have it down. If you're not sure, just use the calculator, by the way. Now, let's say that you didn't notice that. Okay, so you may proceed and say, well, I know 32, and then you'd have 4 and 8. And 4 and 8, it's not divisible by 6 or 5 or 7. So that's actually all the factor pairs. And then you can see also that 4 is its own perfect square. Now, we don't want that set because 4 is not the biggest perfect square, 16 is, so we're not looking at that one. So in other words, I'm going to take 32, and I'm going to split it up into those two factor pairs, 16 and 2. Like this, because the square root of 16, I know, is 4. And then the square root of 2, that's not a perfect square, so we're just going to keep it there. That is done. And you notice that it's the same exact answer that we got here. This one does take a little bit more experience because you have to have your perfect squares memorized, right? 16 and 4. 4 would work. You could have the square root of 4 times 8, but it's not considered fully simplified because 8 can factor into another 4 and 2. So that I'm kind of using the prime factorization to show that. So you'd have to be careful with this method because if you don't find the right factor pair, then you may end up not having simplified it completely. So now to relate this to what we saw yesterday, I'm going to take 32 and kind of compare it to what we saw in yesterday's lessons. Geez, well, wasn't it 6.2 or 3? So 32 we could write as a exponent, right? That square root right there would be the power of 1/2. And that's not 32 times 1/2, of course. It's 32 to the power of 1/2, which is very different. But 32, just like we can see over here, it's really 2 to the power of 5, right? So here's what I can do, is I can take 32 right here and make it, instead of 32, I can make it as 2 to the power of 5. And this would be to the power of 1/2. See, now I have exponents that I can multiply because of the parentheses, and then I end up with 2 to the power of 5/2. That's 5 times 1/2. Now, is that helpful? Perhaps. But what I would want is exponents that just really come out as 1, which would be, so I'm going to split this up, and this is where students start to hate this. It's like, oh, I can change it into 2 to the power of 5 over 2. That's great. We changed the base, and it feels good. But we're not finished. So 2 to the power of 5 over 2, I'm going to use more steps perhaps than you'd probably want to do. But that would be the same as 2 over 2 plus 2 over 2 plus 1 over 2. And then you'd have 2 to the power of 2 over 2 times 2 to the power of 2 over 2 times 2 to the power of 1 over 2. Oh, yeah, so some students are like, how the crap did you get that right there? So I have common denominators of 2, but I split 5 up into 2, 2, and 1. Why did I do 2 and 2? Because it matches the denominator. So that right now, that's what I'm going to do, is I'm going to take that, the 2 over 2's, which is really just 2 to the power of 1, and then I'm going to multiply that by another 2 to the power of 1, and then multiply that by the 2 to the power of 1/2. See, like this, a little bit more space.
This is the method that you use?
So,
I understand it, but I don't.
yeah, well, it's you can enjoy it someday. 2 to the power of 1 times, really it's just 2 times 2 is 4. See that? And then you got this 2 to the power of 1/2. Now I will change it back into a root so that it's in the format that the assignment wants. Boom. Now, yeah, you can see this way, it takes a lot of thought. Maybe you could say it takes a lot of experience. I don't know. You get to decide on your own. Like, you could have split this up over here. You could have taken that at that point, and then made it 2 to the power of 2 to the power of 2 times 2 to the power of 2 times 2, and then taking that to the 1/2. I'm not really encouraging this method right here, just because I think that takes a lot more experience than we have right now. But if you can, like if you can understand this from what we saw last time, then this may make a little bit more sense to you. I don't know. I prefer this method though. This is the one that I'm going to be using almost always. So again, if you like the prime factorization, that's good. If you want to just find the perfect squares, I should have labeled that. And then this one right here was just using the exponents. None of these are formal. Well, prime factorization is a formal method, but if you went to another teacher person or math nerd and said, why don't you use a finding perfect squares method, they'd be like, what the crap are you talking about? Because it's not a formal, as far as I know, it doesn't have a formal name to it. I could be wrong about that, being a math nerd, but I just don't remember that there is. There is a fourth method.
No.
It's my favorite method. It's called calculator method.
That's the fourth method.
Well, I'm still going to show it. I mean, it's called calculator method. It's a calculator method. Calculator. Let's see if I can spell that right. Calculator method. So here's what you're going to do. You're going to type in the square root of 32 and push enter. So, yeah, that's what, you got to get the square root though, right? So that's the second. And then you're going to push, this is a square root, so you're going to push x squared. And then you type in 32, then you push enter, and you'll never guess what the calculator gives you. It says 4 times the square root of 2. So I'm going to be using this method just so we can have some work, but this is a really nice way to at least check what you're doing, whether you're using prime factorization or finding the perfect squares or this exponent stuff. Calculator is at least a great way to check.